Hi everyone. In this video, I'm going to be going over group actions. So group actions are kind of the cornerstone of sort of the usefulness of group theory. They pop up really everywhere, and when group theory is first introduced to someone, you often hear it's about symmetries, it's about whatnot. And like when you study things like permutations or dihedral groups, stuff like this, where you're looking at the symmetries of some object. Really, the group there is acting on some set. Say, for instance, if you have a triangle, like an equilateral triangle, then there is some group G which represents its symmetries, namely you have rotations and reflections, right? Um, and really what the group is representing, it is representing an action. The group is an action on S. Group actions also show up in, beyond these sort of elementary little examples, right? They show up in representation theory and manifolds and so on and so forth. So they're really a powerful idea for groups. Now, before I get into things, there's kind of some things I want to say about this. Um, uh, One thing is that a very, very important results that come from group actions are the silo theorems, or Silo's theorems. And what the Silo's theorems tell you is they tell you information about certain subgroups of a group based on the prime factorization of the order of the number of elements in your group. Um, and it's a very, very beautiful set of results. However, I'm not going to be covering this. Now, in my main reference, which is Undergraduate Algebra by Serge Lang, he goes over Silo's theorems right after the section on group actions. Um, it's just kind of involved, and I want to cover a lot of ground without getting too in depth. Like I feel like Silo's theorems could take up possibly 2 videos. It's definitely a topic I could return to in the future. But for this main series, I kind of want to keep it more to just the essential parts of abstract algebra. And Silo's theorems, while they are incredibly beautiful and obviously like a surprising connection to number theory and finite groups, um, they're not, super essential for understanding other things like Galois theory and so on and so forth. Like, they're kind of an isolated result. I've never really seen them pop up that much anywhere else. So without further ado, we're going to be talking about group actions. So what is a group action? Well, let's say we're given G is a group, and S is a set. Then an action of G on S is a homomorphism, which I'll denote as pi, from G to the set of permutations of S. Okay, so remember, a permutation is just a bijection from S to S. Okay, so for every element of G, we have some permutation of S, some bijection from S to S, and the homomorphism tells us essentially that the permutation corresponding to the product of two group elements is the composition of the two bijections, the two permutations. Now, instead of instead of, say, pi of g of s, right? So here pi of g is the permutation corresponding to g, and then s is some element in s. We often write gs, right? So we write it in a very, very compact notation when the context is clear. Now, obviously, we can see that a group acts on itself by multiplication and conjugation. So these are examples. So when I mean multiplication, I mean literally in this notation, if S is equal, so when I say it acts on itself, that means that our set S is just the group. And so the multiplication is that, right, pi of g acting on some other group element h is quite literally the product g times h, right, the group product. And then conjugation, I'll use the letter C, is when you multiply by the element on the left and then by the inverse of that element on the right. And this is indeed a homomorphism because notice that G H1 H2 G inverse is equal to G H1 G inverse G H2 G inverse, right? We can introduce this factor, G inverse G, because this is just the identity. Okay. So these, by the way, these permutations of G, well, these happen to, well, I don't think this applies to all permutations, but in the case of these kind of special actions where, you're using group properties in such a way that, how should I say? They're not just bijections, but these are also homomorph. So we know that pi is a homomorphism in terms of the variable g. But these are also homomorphisms in terms. Oh, you know what? Sorry, I demonstrated the wrong thing here. I was getting out of myself. So what I should have shown here is that C is a homomorphism in terms of g, meaning that if we have g1, g2, h, and then the inverse is going to be g2 inverse g1 inverse, and then you can see you have this composition. This is C of g2 of h, and then this is C of g1 of this. Okay, so, but yeah, with these group like multiplication and conjugation, we see that they're also homomorphisms in terms of h, right? They're not just set permutations on the set of group elements, but they're also homomorphisms. And so we call this an automorphism, which is just an isomorphism from a group to itself. So obviously there's always the quote-unquote trivial automorphism, which is just, sending each group element to itself. And I believe there's a result like every group has some non-trivial automorphism, and I proved this in a video like abstract algebra problem solving series or something like that. I called it a series, and I only ended up making one video, but I'll probably return to that at some point because I need to. They're actually I'm pulling them from like a test bank, and I have to prepare for a test in like a year or two. But yeah, if you go to this video, I think the result is that like every group of order uh, 2 or more has some non-trivial automorphism. So anyway, these special group actions are actually homomorphisms. Uh, so pi and c are group homomorphisms from G to the group of automorphisms of G. Now, namely what this means is that in the case of C, okay, let's just focus on C. Once we have a group automorphism, or sorry, not, once we have a group homomorphism, we know that the kernel of C is normal, right? This is a result we've proved. Now, what is the kernel of C? The kernel of C is the set of G in G such that GHG inverse is equal to H for all H in G. Okay, so why is this? Why am I saying this? Well, the kernel, right, is the set of group elements in our domain which map to the identity, right? The identity automorphism just means whatever goes in, which is my H, comes out, which is right. So, so the kernel is the group elements which, when I conjugate, I always get the same thing back. Now notice if I multiply by G on the right, I get GH equals HG. So this is the set of G which commute with everything in G. And this is called the center. It is typically denoted by Z of G. So the center of G. And so we can see that since we've derived this as a kernel of a group homomorphism, the center is normal. Okay. It is also an abelian subgroup, right? Notice that if I take two elements in the center, by definition, they commute with everything, so they commute with each other. So any two elements in Z of G commute, so Z of G is an abelian subgroup. All right. Now let's get back into some more technical definitions. So we define the orbit of S in S is the set GS. We denote it like G, kind of like the group G times S, which is the set of GS where G ranges over all elements in G. Now, of course, we don't necessarily have to have that all of these are distinct. In the case of, these nice things, right? They're distinct, but you can have, of course, that two group elements sending some element in the set to the same thing, right? That's a possibility. For instance, obviously the the identity element is going to map to S, right? It's going to map S to S. And then we can consider, okay, if there is some permutation of S that we can achieve by our group action that fixes S, then that will also map S to S, right? So for example, with the triangle, okay, so the identity leaves these 3 points fixed, right? But then there's also this reflection, which swaps these 2 points, but leaves this one fixed. So if you call this S, then, you know, you're going to have, clearly you're going to have that GS is equal to S for more than one value of G. So the elements of the orbit don't necessarily have to be distinct. Well, I mean, my point is that you can't just say right away that if G1 is not equal to G2, then G1S is not equal to G2. That's all I'm trying to say. It's kind of late at night. I probably shouldn't be making a lecture video like this. Okay. As a special side definition, the orbit of an element under C of G, or I should just say C, is, so this conjugation map that we defined earlier is called a conjugacy class. So in other words, they're group elements which can be related to by some conjugacy. Oh, and that's another thing, is that if T is some element in the orbit of S, then T is equal to GS, right? So if Y or QR, I'll let let's say T and R are in GS. So T and R are elements of the orbit. So let's say T is equal to GS and R is equal to HS. So that S is equal to H inverse R, right? And this implies that T is equal to G H inverse of R. So in other words, if I have 2 elements in the orbit, then they differ by the action of just one group. This is one group element, right? GH inverse is just equal to some group element G prime. So the 2 elements of the orbit are related to each other by some group element. Okay, so that's the idea of an orbit. Now we have the idea of an isotropy group. Okay. The isotropy group of an element S and S is, the notation gets a little weird because now it's G with the subscript S. And these are the G and G which leave S fixed. Okay. So again, going back to this triangle example, we see that, oops, sorry. We said that if this is S, then clearly the identity is always in an isotropy group. Well, for one, it has to be a group. Well, you need to prove that it's a group, but it is a group. So it contains the identity, and then it also contains this reflection, right? Because that also left S still. And it turns out those are the only 2 elements of the symmetries of an equilateral triangle that leave this point fixed. And so the isotropy group is just consists of the identity and that reflection. So it's an order 2 group. So I believe that for actually I forget. Oh well. So the problem now is that uh, so GS is a subgroup of G, right? So let's check why this is a group, right? Well, if I know GS equals S and HS equals S, then GHS is equal to G of HS. HS is S, so this is GS, which is S. Okay, so that just proves it's a group. Okay, so GS is a subgroup of G, right? But it's not necessarily normal, right? Not necessarily normal, right? So if I take like H inverse, where H is not in GS and G is in GS, and I apply this on S, this may or may not be equal to S. So let me try and think of an example with this thing here. Now, I think it is normal here. Is that true? No. Okay, so let's consider, so here's our triangle. Let's say G is this reflection, and then H is a rotation around this axis. So first we go H inverse, so that's a rotation in this direction. Okay, so like this. So now this is S. And then we apply G. So this is H inverse. Now we apply G, takes us, swaps these two. So then S, S is over here. And then remember H is a rotation like that. So S is going to end up being over here. So this does not fix S. So G sub S is not necessarily normal, even in this small example. However, we do want to look at, however, we still look at cosets of G sub S and the factor space G by G sub S, right? So this isn't necessarily a group, but we still want to look at, you know, the partition. G a subgroup is always going to partition a group into cosets, right? It's just that when it's normal, that partition itself forms a group, okay? So, let's say x and y are in some coset of G sub s, okay? Then that means that x equals GH1 and y equals GH2, where H1s equals H2s equals S. Then Ys is equal to GH2s, which is equal to GS, right? Which is equal to GH1s, right? Well, I could have cut the chase here because I already said H1s equals H2s, which equals XS. Okay. So if two elements in a coset of G sub S will have the same effect on S. Thus, the map F from the vector space to S given by f of x g sub s, let me do g sub s, equal gs is well defined. Right? Remember this nuance here that whenever we define a map from a factor space or on a factor space, and we define the map implicitly using this representative, this coset representative, right? We have to show that it doesn't matter what two representatives I choose. I'm still going to get the same output, and that indeed shows here. If I choose any two elements in a coset, then they have the same effect on S. Okay, so what does this map allow us to say? We want to say that this map gives a bijection from G by GS to the orbit GS. So clearly GS, the orbit of S, is contained in S, right? It's just all the points in S where little s can be moved to by G. Okay. And we know, right, GS, well, let's say T is in GS. This implies T is equal to GS, and therefore T is equal to f of GS, which is an element of the image of f, right? So thus, f is surjective onto GS, right? Because by very definition, right, we're mapping onto an element which is equal to some group element acting on S. So this is clearly an element of the orbit. And furthermore, any element of the orbit can be represented by, can be equal to an image of F. Now we just have to show that F is injective. Now remember that F isn't a homomorphism because, well, neither of these two things are groups. Well, of course, yeah, neither of these things are groups. So, so we just have to show it's injective the good old-fashioned way, which means that if f of GGS is equal to f of HGS, this implies by definition that GS equals HS. Thus, H inverse GS equals S by multiplying on the left by H inverse. So this means that H inverse G is an element of G sub S, right? Oh, and I should mention this isotropy group, I was missing the word. This is also called the stabilizer of S. That's a much more common word. However, the book I'm referencing uses isotropy group. So this came to me. Right, so H inverse G is equal to G sub S, right? Thus, G is in H G sub S, so G sub S is equal to H G sub S. The reason being is that since we have that little g is obviously an element of little g times little GS because G sub S contains the identity element, so this contains GE, which is just G. Therefore, these two cosets are not distinct, and remember, cosets are either distinct or they're equal, right? They partition G. So if they're, sorry, not distinct, disjoint, that's the word I'm looking for. So we have that they're not disjoint, therefore they're equal, and this shows that this F is injective, right? We've shown that if the image of two elements of F are equal, then the elements must be equal themselves. Okay. So what does this tell us? Thus, the order of the two sets have to be equal to each other. Right? But the order of a factor space is just the quotient of the two orders of the groups. So this means that the order of G is equal to the order of the stabilizer times the order of the orbit. And this is often called the orbit stabilizer theorem. And there's a lot of wonderful things that you can do with this. So again, I'm sorry that this video is probably a little bad because it's late at night and I'm not thinking clearly, but hopefully you gained something nonetheless. And I hope you watch the next video.